Stars are awesome. Since mankind first became able to comprehend our existence, we've looked up at the night sky and seen these distant glimmers of light, and they've shaped our culture, religion, and scientific progress. While you can only see a handful of stars with the naked eye, the universe has more stars than one could possibly imagine, shining and radiating light and heat throughout entire galaxies, and they provide the essential warmth that cradles life. All life on Earth owes to the sun. Even the animals at the sunless depths of our ocean would not exist were it not for the sun's gravity and the dust that once surrounded it forming the ground we now stand on. But putting its existential considerations aside, how do stars actually work? Why is it that the universe is so full to the brim of hundreds of sextillions of stars? What makes them so common, and why are they so massive and powerful? Well, to understand the answer to these questions is to understand creation, and the story of a star from birth to death is unparalleled in astronomy. Today, we'll be journeying back billions of years as we uncover the mysteries, wonders, and timelines of our own sun and the other stars that characterise our galaxy and the universe. Firstly, before we begin to look at how they form, what exactly is a star? Well, in short, stars are massive spheres of matter in plasma state, essentially a giant continuous explosion of molten soup, held together by its own gravity. Stars are powered for the vast majority of their lives by nuclear fusion, an energy generating process we are trying to recreate here on Earth to solve our energy demands. For about 90% of a star's life, it turns hydrogen into helium at its core, and the energy this releases moves to the surface and emits stellar radiation. When it comes to our own sun, we call this emission solar winds, light, heat and matter radiating across space over billions of kilometres for billions of years at a time. Stars are the most massive component of any given stellar system. Like our own solar system, the sun accounts for over 99% of the mass of everything in our solar neighbourhood, and as such we often use measurements of the sun's mass to estimate and categorise the weights of various other astronomical features. The mass of our sun is approximately 1.989 times 10 to the 27 tonnes, which is a number I'm not even going to try and pronounce. However, this figure characterises one solar mass, a unit of measurement we use to assess the mass of other stars to that of our own, and we'll be using this measurement a lot today. There are estimated to be as many as 300 sextillion stars in the visible universe, that's 3 with 23 zeros. Approximately 2 to 400 billion of these stars lie within our own galaxy, the Milky Way, and each mature galaxy usually has anywhere between 100 billion to 100 trillion stars. Around 2,000 of the stars in our own galaxy are visible from Earth in the night sky, with these particularly bright, local and luminous stars being grouped into shapes that resemble humans, objects and animals, known as constellations, which are really useful when it comes to mapping the positions of these nearby stars. Stars can form in groups of dozens, hundreds or thousands, and these can form star clusters. Thanks to the gravity of these clusters, and with a bit of help from dark matter, these clusters then combine to form dwarf galaxies, and the dwarf galaxies then combine to form spiral galaxies, such as the Milky Way. Spiral galaxies retain the hydrogen and helium gas clouds that formed the earliest stars, and as such these spiral galaxies are essentially gigantic star-producing factories. These galaxies then collide to form giant elliptical galaxies, where some of the highest concentrations of stars in the known universe are found. But thinking smaller than star production on a galactic scale, how does an individual star actually form? Well, its life cycle is fascinating and can be broken down into 4 main stages. Star formation begins with molecular clouds. These are clouds of dust and atoms that have been around since the earliest days of the universe, and they have higher densities than their surrounding space, and so are held together by their own gravity. These clouds consist of mostly hydrogen, the most abundant element in the universe, and usually about a quarter helium, with a small fraction consisting of a few other heavier elements. These clouds come in many different shapes and sizes. One such form is nebulae. The Orion Nebula is a giant star-forming region in the constellation of Orion's Sword, which is visible from Earth. Other areas of star formation include the Interstellar Medium, clouds of hot gases and atoms that occupy the space between stars in galaxies, and in certain regions of colliding galaxies where multiple hot gas clouds collide, invariably making them much more productive, often forming what is known as a starburst galaxy. No matter what form these clouds take, eventually they collapse into a dense core due to their own gravity, and this gravitational energy then turns to heat. When this collapsing cloud reaches a relatively stable point, the embryo of a star forms, known as a protostar. These infant stars are then cooked in this giant gaseous oven forming around it, trapping more hydrogen and helium within the core. This process of incubation in this manner takes about 10 million years, and when the protostar is sufficiently developed, it begins to emit plumes of gas, which, alongside external radiation, helps to drive away the gas clouds around the outside, essentially the shell of the star. These shell gases that are driven away are mostly dust, and are ejected outwards but still orbit this new star. This dust begins to clump together, forming rocks, and these rocks smash together to form planetary embryos which have the potential to become planets. Earth was formed in this way after the Sun formed, and complex carbon chemistry did the rest. So essentially, we all came from stardust once. This is the beautiful process that fragments massive gas clouds, turning them into dozens, hundreds and thousands of new stars, with child planets to watch over and keep warm. These stars are then ready to enter the next phase of their lives. However, not all stars get this far. Those stars with a particularly low mass, more comparable to the mass of Jupiter than the mass of the Sun, are unable to sustain nuclear fusion of hydrogen in their cores, an essential process for a star in the main stage of its life. These light stars can, however, fuse lithium, and instead of becoming a star, they become what are known as brown dwarfs. Contrary to the name, they often appear magenta in colour, and often sit somewhere between extremely large gas giant planet and extremely light mass star. They also typically have no difference in structure between their cores and their outer layers, and so these failed stars never get to become the giant radiating beacons we see in the night sky. But for those that are massive enough to sustain their fusion reactions, these stars burn away their incubating molecular ovens and enter the second and main stage of their lives, the thermonuclear fusion stage, otherwise known as the main sequence. The main sequence accounts for about 90% of a star's lifespan, and is the point when fusion begins to take place, with the vast quantities of hydrogen that has been trapped in the core being fused into helium, releasing massive amounts of energy. This is what gives stars their immense heat, blinding light and incredible radiation that travels billions of kilometers across the near vacuum of space. A star that has just entered the main sequence is usually in the form of a dwarf star. The Sun is a main sequence yellow dwarf star currently. These stars are small compared to some of the other older stars, and contain much more hydrogen than they do helium. However, fusion converts hydrogen into helium, and so the share of helium within the star begins to rise. This increases not only the brightness and temperature of the star itself, but the rise in helium also increases the rate of fusion in a somewhat compound process. This process, coupled with the emission of solar winds and radiation, causes some mass to be lost. However, this usually equates to only about a fraction of a percentage of the total mass over a star's entire life, so it's nothing to worry about. However, much more massive stars can lose a more significant percentage of their mass during the main sequence and beyond because they are much less efficient. How long the main sequence lasts for depends on the size and mass of the star and the amount of hydrogen that star was formed with. Our Sun is expected to live for around 10 billion years, whereas some supergiant stars with more mass will be considerably less stable and last nowhere near as long. The smallest possible main sequence stars are known as red dwarfs, and these can fuse all of their mass fairly efficiently, and so stand to live the longest. We don't know how long for sure, but we theorise that it could be up to 1 trillion years. When these smaller and less volatile stars have burned up their hydrogen, they will collapse into white dwarfs and the temperature will fall, circumventing any other post-main sequence process. As for the more massive stars, these are less efficient and less stable. They fuse their hydrogen at a certain pace and can last for billions of years, but after the hydrogen fuel at the core has been used up, helium will start fusing into carbon, and this is where things start to get interesting. If a star is approximately 40% of the mass of the Sun or above, then when the hydrogen fuel within the core is exhausted, the star will begin to fuse hydrogen outside of the core, which is now all helium. Heavier elements are being fused in the core as a result, and these newly fusing outer layers expand and cool down, dramatically increasing the star's size and giving it a red colour. It has entered the red giant phase. This is the stage we all love, because it is the stage that forms the titans of the galaxy. The size of the star in its red giant phase depends on its mass, But regardless, it is ironic to think that when a star grows to become a giant, it is actually in the stage of its life where it's starting to die. Our Sun is no exception either. In an estimated 5.5 billion years, the Sun will exhaust its hydrogen and balloon in size, expanding to about 250 times its current diameter, while ejecting over a third of its mass. This will mean that Mercury and Venus will both be engulfed and destroyed by the giant, and while Earth may just escape this fiery ending, the planet's surface will be fried, and surface conditions will become similar to that of Venus, and will never be able to support life again. Red giants aren't the only things that can be formed in this post-production phase either. Stars with a mass several times larger than the Sun will expand so much that they are classified as supergiant stars, and stars with a mass in excess of 9 solar masses can expand to form blue supergiants before evolving into red supergiants. If the star is abnormally massive, for example much more than 9 solar masses, we tend to classify these as hypergiants. Particularly massive stars can also evolve to become what is known as a Wolf-Rayet Star, which emits elements heavier than hydrogen and helium from the core due to the intense mass loss after the main sequence. The biggest known star in the galaxy is commonly attributed to the beast that is Au.Ra, a more recently classified giant of the Milky Way. Before that, it was VY Canis Majoris, which may still actually be the largest star we've ever discovered, because all of the stars estimated to be larger have much less accurate estimates of their radius. But, taking Au.Ra as an example, it is estimated to have a radius of about 1,700 solar radii. That's 1,700 times the size of the Sun, which sits at about 1.3 million kilometers in diameter. This mind-boggling size means that were you to place Au.Ra at the centre of our solar system, it would engulf every planet, asteroid and moon as far out as Saturn. To put that size in another kind of perspective, if you were to fly an aeroplane around its surface at just under 1,000 kilometers an hour, it would still take well over 1,100 years to circle it just once. Some of the biggest stars we've ever discovered have crazy numbers associated with their size, and given that this is just within the immediate vicinity of the Milky Way, you have to wonder what else could be lurking out there. As mentioned, even though these stars are awesome, they are in the dying phase of their lives. As the outer shell layers fuse hydrogen in these massive stars, the core becomes heavier and its temperature rises. When the temperature is at a high enough level, helium fusion begins violently, which is known as a helium flash. This causes the star to shrink in size very quickly, and even with some variations of the process, all red giant cores eventually become degenerate as the star begins to die, entering the final fantastic phase of its life. After a star's core becomes degenerate, it starts to shrink. The radiation from the surface increases dramatically, creating pressure on the outer shell, which in turn strips back the outer shell layers. Depending on the mass of the star in question, a number of very different outcomes can then occur. If what is left of the stripped back star is now less than 1.5 solar masses, then the star will shrink to a size comparable to the Earth and will become a white dwarf. White dwarfs are not heavy enough for gravity to continue compressing them, and the electron matter inside the star is no longer in plasma state. Eventually, white dwarfs burn themselves out, emitting no more light or heat, and enter a theoretical stage known as a black dwarf, or a cold star. The lightest stars end their lives fairly tamely. After they have finished their main sequence, they become far smaller, and from there they just fade away. When it comes to more massive stars, these can start to produce iron in their cores by fusing helium into heavier elements. If the iron core is above 1.5 solar masses, then the shrinking and receding star will no longer be able to support its own mass. It will begin fusing heavier elements, iron, nickel and cobalt, and this will mark the final moments before a fantastic death. No heavier elements can be fused, and so no new radiation is produced to counterbalance the gravity of the core keeping the star intact. The star can no longer keep itself hot enough, and electrons will be driven into protons, forming neutrons, neutrinos and gamma rays, causing the star to violently implode. This collapse causes a shockwave, which causes the outer layers of the star to blow up in a brilliant explosion known as a supernova. Supernovae are among some of the brightest things in the universe. Sometimes they are so bright that they even outshine their entire galaxy. The explosion disperses the star's outer layers, leaving a remnant in the surrounding area. These remnants are called nebulae. One such stellar ghost is the Crab Nebula. In fact, this is exactly what is predicted to happen to a nearby supergiant star in the Milky Way very soon. Betelgeuse is an extremely luminous red supergiant star over 900 times larger than the Sun, located 640 light years away from Earth. It is one of the 10 brightest visible stars in the night sky, and is highly unstable and beginning to shed its outer layers. When it finally enters the ion fusing process and implodes, it will go supernova and its brightness will rise to billions of times brighter than our Sun. Documented cases of supernova explosions have only happened a few times throughout history, and none have been as close to us as Betelgeuse is. So, when it finally does blow its banks, the resulting brightness will be visible from Earth during the daytime and the nighttime, with some predicting that it will even outshine the Moon for the best part of a year. Given that the light delay is over 600 years, it could have already happened and the light is travelling towards us now, so there's a slim chance that you or I watching this video may be able to witness Betelgeuse go supernova and outshine the rest of the galaxy in our lifetimes. As for when it will happen, well, we simply cannot tell. After the brilliant visual display of the supernova has occurred, the cores of these stars can still continue to evolve. In some cases, the core will collapse in on itself and form a very dense, comparatively minuscule object with an immense gravitational field relative to its size, known as a neutron star. What was once a massive star capable of engulfing millions of kilometres collapses in on itself to form an object no more than 30 kilometres wide. In some cases, these celestial bodies will rotate rapidly and sometimes emit beams of radiation detectable from the Earth, called pulsars. It was through this phenomenon that in 1967 a signal named LGM1 was discovered, a radio signal from a pulsar that was initially attributed to a transmission from an alien civilization. Most neutron stars have such strong gravity fields that, were you to drop a teaspoon from shoulder height to the ground while standing on one, the spoon would reach speeds in excess of 22,000 km per hour before it collided with the ground. However, that still isn't the most extreme thing massive dying stars can form. Not all post-supernova stars collapse to form a dense neutron star, some take it a step further. If the stripped back core in question is in excess of 4 times the mass of the Sun, then the resulting force of the implosion will be so great that it will compress the entire core into a single microscopic point with near infinite density, known as a singularity. The resulting gravity field is so strong that, past a certain point, not even light can escape. The massive collapsing star has now formed a black hole. Black holes are some of the strangest things in the universe, and are the ultimate all-consuming eventuality for the most massive stars. While these black holes aren't usually the supermassive black holes at the centres of galaxies, they can still achieve some pretty impressive sizes. Whatever happens to a star when it dies, it's never usually boring. So there you have it. We've now covered the life cycle of a star, from its formation to its death. These massive thermonuclear explosions are responsible for shaping so much of the universe you see around you, where galaxies are the legions of the cosmos, stars are the centurions. But the question is there a size limit that stars cannot exceed? Well, theoretically yes, there should be a size limit for stars, and this is not due to the mechanics of the star itself, but is more to do with the star-forming molecular clouds. These clouds cannot exceed a certain mass when incubating stars, or they would lose their star-forming properties. So, with this in mind, some papers have speculated that the upper bound for stars should be about 150 solar masses. But then again, we've discovered stars, such as the blue hypergiant Pistol star, which are estimated to be closer to 200 solar masses, so no one really knows for sure. Ultimately, we can conclude on an upper bound limit for mass, but when it comes to size, there are a few more variable factors. The largest known star is about 1,700 times the diameter of the Sun, and some predict that cool supergiant stars could grow to as big as 2,600 times the Sun's size, but others dispute this. Principally, there is no absolute cutoff point that we can set the benchmark at because we simply don't know enough about the detailed long-term process of star formation and evolution. And who's to say that in the future an abnormal star won't be formed which is greater than any other star that has ever existed? The idea of an upper size limit hinges on the assumption that the number isn't fluid, but we simply don't know. and even a survey sample of an entire galaxy doesn't really provide the clear picture we need to gauge a better understanding of star metrics. However, every discovery we make challenges old ideas, and so the only way we can ever conclude on star size limits is to continue to discover, observe and research these giants of creation. Stars are truly some of the most wonderful things in the universe. With our wealth of knowledge now, it's easy to lose sight of them as we think bigger, galaxies, galaxy clusters and the rest of the universe. But when you break a galaxy down to its key component, you see the root cause of so many defining features of our universe. All because gravity attracts hydrogen and helium atoms together, and given enough time, complex processes produce these brilliant stellar firework displays. From the dwarfs right up to the hypergiants, each star has its own story to tell, its own solar system, and its own possibilities for supporting life. And with 300 sextillion stars out there, and hundreds of sextillions more beyond the boundary of the observable universe, the possibilities really are endless.